All right, so now we're going to talk about the three different types of intermolecular forces there are. And it turns out that these groups that I've chosen here each represent one of the main types, or one of the three types. And the first one I want to talk about here is, let's start in the middle with the ketones. Now, what makes a ketone is this carbon-oxygen double bond here. So think back to when we were talking about molecular structure. Carbon-oxygen bonds are polar. Carbon-hydrogen bonds aren't. So this molecule is polar. You have one polar bond, a bunch of nonpolar stuff. It ends up being polar. So it has an area of partial positive charge. In this case, it's going to be this carbon, and partial negative charge, that oxygen. And that's the key for the intermolecular forces for molecules like this. Polar molecules exhibit an intermolecular force called a dipole-dipole interaction. So this is a simple version right here, that you've got your generic polar molecule. It has an area with a partial positive charge and an area with a partial negative charge. And so if it has a friend, then the area of partial negative charge will be attracted to the area of partial positive charge, and vice versa. Now, when you have a whole bunch of them together, you've got this really complicated set of attractive interactions. Those are the red lines, and sets of repulsive interactions between areas of like charge. But if you arrange things correctly, the attractions are going to outweigh the repulsions, and overall there is a net attractive force. These molecules are drawn together and they will form a liquid or a solid. So this is due to the interactions between molecules that have a permanent dipole moment, polar molecules. Now, for molecules of similar size and mass, the strength of these interactions increase with polarity. So that means that basically the more polar the molecule is, the more polar the bonds are, the stronger this interaction is going to be. So the more polar molecules will have a stronger intermolecular forces, higher boiling point. So hopefully that made a little bit of sense. So the question is, what about the alkanes? These are made up of exclusively carbon-hydrogen single bonds. And when we started talking about molecular structure, you were told that these are nonpolar, which means the molecules are nonpolar, because if the bonds are all nonpolar, remember the molecule can't be polar either. So what interaction exists to bring these molecules together to form a liquid or a solid? To explain that, I'm going to use as an example quite possibly the most nonpolar thing there is, a helium atom. So helium atom all by itself, alone in the universe, has two protons in the nucleus, 2 electrons, and those electrons, left to their own devices, adopt a perfectly spherical distribution. So no partial negative charge, no partial positive charge, nothing. That is as nonpolar as you can possibly get. But the universe is more than just a single helium atom. So let's say it has a friend, and that friend gets in a little bit closer. And as they get closer and closer, what happens is these electron clouds interact with each other. Now, electrons all have negative charges, so they kind of repel each other. So what happens is that as soon as the electron cloud on helium atom 1 feels the repulsion from the electrons in helium atom 2, they distort. And those electrons spend a little more time on the other side, right? So way back here. So on this back end of helium atom 1, you've got a partial negative charge that sets up, and you've got a partial positive charge at the front end, because the front part now has less electron density than it did before. Now simultaneously, the electrons in helium atom 2 react to that. And that now they're going to be skewed in this direction as well, because they're a little more attracted to the now partial positive front side of helium atom 1. So they get shifted this way, which makes this end of helium atom 2 gives it a partial positive charge as well. And so both of these now have a temporary or induced dipole moment. It's not permanent. It doesn't exist when the helium atom is just by itself, but the interaction of two or more atoms together create this dipole moment. Now, this dipole is very weak, but it's the only way that nonpolar molecules can come together to form a liquid or a solid. So these atoms or your generic nonpolar molecule can develop an instantaneous dipole moment. Now, what makes this strong or weak? Well, overall, they're much weaker than the dipole-dipole interactions. Now, these depend on the polarizability of the molecule. So polarizability is a fancy word that says how easy it is for these electrons to get pushed around. And usually, the more electrons something has, the easier it is to do. Our 2-electron helium atom here is about the least polarizable thing there is. It has a very small polarizability. The bigger something gets, the more electrons it has, the stronger this is. This is why the boiling point of all of these things, but the alkanes in particular, increase with molar mass. More atoms, more electrons, stronger London dispersion forces. These, by the way, are also called in some other sources an induced dipole interaction, but I like London dispersions. All right, so bullet points. So the strength or the magnitude of this force increases with this thing called polarizability. And that increases with molar mass. So the heavier something is, the more polarizable it is, the stronger its induced dipole. And finally, this is a pretty low tiebreaker, but the polarizability also increases with molecular contact area. So for example, what I have here is a very, very horrible representation of one form of pentane. It's just 5 carbon atoms in a chain, and it turns out that these chains, when in real life, they're not straight, they kind of zigzag. But this is 1, 2, 3, 4, 5 carbon atoms. So they're kind of in a line. So I'm calling this like the hot dog or the cigar shape. Now, if it has a neighbor, the interaction is this squiggly stuff right here. In that there's that much contact area. And so that's a relatively stronger or relatively strong London dispersion interaction. There's another way to put together 5 carbon atoms, and that is 1 in the middle and 4 attached to it. This is called isopentane. The result of this thing is this molecule is kind of a sphere. And if you envision like trying to get 2 pool balls to touch, when they actually touch each other, there's really only a small point where they're actually contacting each other. So this is effective or molecular contact. This is a lot of contact surface area. This is not much. This is a weak London dispersion interaction situation. This is stronger, and this is why they've got the same formula but fairly different boiling points, because the intermolecular forces are stronger with this shape than with this shape. But that's like the second or third tiebreaker. All right, and that's it for dipole-dipole interactions, for London dispersion interactions. Hydrogen bonding is a little more complicated, so it gets its own video, and I will see you then.